So let's go into a very different kind of talk. And here I will basically have a more dynamical talk about star cluster and free-floating planets itself. So first of all, I present to you Nbody6 massless, which I very calmly tell him to actually give me some answer about where are the free-floating planets in a star cluster. If I dynamically evolve them, where should I find them? And so, in order to answer this, I will first give you some definition. Maybe some of the other ones know already about this, but just to make everyone in the same side. So first of all, the system normally is in a very equilibrium in the sense that typical self-gravitating bodies have the ratio between the kinetic energy and the potential energy is 0.5. That means that everything is in equilibrium. And when I will say supervirial and subvirial, I mean that this cluster is either expanding or contracting according to supervirial or subvirial. Brown dwarf, that we already know and love, will not be considered free-floating planets by me, and you will understand soon why. And the planet mass is not going to be important. I will actually not tell you which the mass it is because of the definition of what happens in a star cluster when you put a free-floating planets in the center. And in my system, all the free-floating planets are primordial, so I already consider them ejected from the host star. And the core radius that I will define also here is where basically the star cluster density drops by half after it. So let's go first in describing what mass segregation is. So mass segregation, as you can see here, is when basically in a star cluster, larger mass and the smaller mass interact together. What happens is that the big mass give some velocity as a result of the encounter with the other one. And since the big mass loses velocity, it will drop in the center, while the smaller one gain velocity and go outside. This is very, very poorly how we describe mass segregation. However, and this is the point that will go on my talk, is that this is not true for planets, because planets are not so much stronger when it comes to encounter. They actually are basically not dominating the gravity. When they encounter with a star, there is no enough exchange between the two to cause a difference in the overall evolution. And as Gomez-Leighton say, basically all the gravity is dominated by heavy population. So bottom methods are, one is published, this one that I'm going to present to you, and the next one is been accepted recently. So maybe one of you reviewed that. So this is my initial condition. So this is very small. I know that there are some missing ones. And in the case there is time later, we can discuss about this. But basically, I put different density here. So I put the same star cluster dimension, you see, the half mass radius, they contain half the mass. And I also added different numbers of stars. We did this for 300 mega years, and in this, we try to understand what happens if we have different density. Different density means more encounter in this case. And therefore, what we expect is there are more encounters, there is more exchange, what happens? So this is the first thing. Here we plot the cluster-centric distance against the velocity square of the planets and the stars. The stars are the right column, and the planet are the left column. And as you can see, there is at 0 mega year at the start of the simulation and at 300 mega year. The first thing to notice is that MLP, so the planets, are considered are in the center of the cluster. This means that after all of the simulation, basically they tend to accumulate more in the center. And star are like this. So this is already a well-known one, but this happens in all the simulation that we have done. So it's a very interesting result. So can I take this one or is someone else? Sorry, because I forgot to look at it. Much better. Thank you. And then we see how the Lagrange radii works. So the Lagrange radii is a term that basically contains how much mass is contained between each shell of the star cluster. And therefore, 0.1 means that there is a certain percentage of mass. So for star, because star have a different mass, this is going to be a little more complicated, but for free-floating planets, like the one that we saw, this is more easy because they have all the same mass in our simulation. So they basically consider massless. And then, and therefore, this is just the number. So it's effectively the percentage. So in the less dense one, we have that, as you can see, there is more noise due to be very smaller number of star and free-floating planets. And in here, you can already see that the 0.1 and the 10% here, the planet tend to orbit around. And then the 50% stay, which at the start was giving similar evolution compared to the other shell, then it tends to stay below the 50% of the star, and so it remains bound there. 90% is reached after a while due to the evolution of the star cluster that become larger and therefore it stays like that. If we put more density, so basically we put 10 times the star in the same volume, we see that this process is actually more constricted, and the 1% they have similar files, but the 10% is well at the start already behind, and then the 50% is even reached by the stellar one. So basically speaking, denser cluster retains free-floating planets much more easy than lesser dense clusters. And both the cluster, as I said at the start, they retain the free-floating planet. A similar result can be also seen here by the number, how the distribution of ejected planets is here, in which we see that basically it is more linear in the ejection percentage in here as compared to here. And we have that in here, there is much more percentage of ejected free-floating planets compared to that. And this is because, as I tell you before, we have a much more denser star cluster. As for the velocity, that is maybe quite interesting also for you, we can see that it is much faster in denser star cluster due to free-floating planets having more encounters. And as you can see, we have that the velocity of star is 3.6 and 11 for the smaller, denser cluster. And it's on the order for free-floating planets is a little slower here, but anyway on the order of 10 kilometers per second, which is quite an interesting result. Thank you. So I will hurry up a little because already 5 minutes left. So in this is the work that has been accepted recently. So in here, sorry to hurry up, but we use different densities. Different initial energies. So one is subvirial, one is supervirial, and one is in virial equilibrium, if you remember the definition at the start. And as you can see, while they are different at the start, you don't see my here. You see the one that is more has more velocities, more velocity because it's expanding and is gradually becoming less. They have more or less the same distribution at the end. In this, so I will probably just skip those because in here, basically, we have the very nice result that basically the shells of the free-floating planets in all the cases tend to retract. And so basically the planets around 1 giga-year tends to go back in every case. This is in 50%, 20 here, and also here. And you can see here all of them together, in which there is an initial expansion and contraction due to the fact that we choose different energy distribution at the start. And this is basically very fastly removed. This is quite interesting because basically if we have a grid velocity distribution or not, this is completely removed in less than 1 mega-year. While for the external part, as I told you before, we have that actually we lose, the free-floating planets tend to go back in. But one more interesting one is that, as you see, the one with the highest velocity free-floating planets is actually ejecting a lot of free-floating planets at the start. And it's even more relevant if we just go at half of the simulation, in which you see inside 100 mega-year, basically 60% of the total ejection of free-floating planets is already done. And in this cluster, although we lose actually a lot of free-floating planets, around 60% after 1 giga-year. Therefore, we should actually see a lot of non-cluster free-floating planets ejecting by these objects. On the velocity of the skipper themselves, we have a very similar velocity skippers, although that in the 0.70 model is already around 2 mega-year. And in here is the last result that I will show you, is that brown dwarfs are actually basically like stars. They are actually dynamically evolving like stars. And we see that there is a mixing in these regions, because instead of going like this is the same model with floating planets instead of a brown dwarf. The inner region are here. You can see they develop in a sense that they orbit around. In here, they're more mixed. And the 50% shell here, you see, they are basically like this. This is because they partially mass segregate some of those, and they partially not. And this is due to the different masses that we encounter inside the cluster. And with this, I come to my conclusion that are basically a condensed version, but the message home that I want to take to all of you is that free-floating planets are taken in the center of the star cluster. And with time, this is always true because, for example, for globular cluster, you will see much more retainment. For example, here we are just on 100,000 stars. While if we see for open cluster that are not so dense, but they are a lot of free-floating planets, we should have a very high percentage of free-floating planets. That's the end of my talk, and I'm happy to answer questions if I'm fine. Oh, I knew that.
So I have a very quick question for you. Just on your statement and the conclusions here, that yes, you generally retain free-floating planets in the clusters.
Yeah.
How does that reconcile with the sort of high ejection percentages that you were talking about?
Okay, so yeah, this is coming from two different things. So, okay. So basically what I meant here is that the high percentage of free-floating planets depend on the energy distribution. You can see that in open cluster, this is always true. But once this, let's say, initial ejection is done, you actually have that more of the rest of the free-floating planets are inside the core. And it's very difficult that they are ejected unless you go to the disruption timescale of the cluster that is later on.
Could the next speaker come up as we take one more quick question?
Do you account for collisions or tidal disruptions of the free floating planets?
Not a distraction, but collision, yes.